Hi! In this video, we're going to understand how two or more nucleon merge or fuse together to create something more powerful and meaningful. So let's start by talking about the word nuclear fusion. Nuclear means the process which involves the nucleus, and fusion in English means two or more entities coming together or merging together to form one single entity. So nuclear fusion can simply define as the fusion or combination of nuclei. Scientifically, nuclear fusion can define as a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amounts of energy. For example, lighter nuclei such as lithium and helium when combined together to form heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nuclei. The word heavier here is placed in terms of energy release, which is usually very enormous rather than the mass. Therefore, the law of conservation of energy is satisfied. Heavy nuclei are unstable due to large repulsive forces between the large number of protons in the nucleus. In heavy nuclei, the Coulomb energy of proton repulsions become very significant, and this makes the nuclei unstable. It turns out that it's energetically more profitable for a nucleus to throw out a stable system of four particles, an example, an alpha particle, than individual nucleons. Nuclear fusion. The energy source that fuels the sun and the stars. Yes, from the sun and stars can potentially be exploited to generate electricity. The process in the sun involves the fusion of hydrogen atoms at extremely high temperature and pressure, but those conditions cannot be recreated on the Earth. But another fusion reaction between deuterium and tritium. In this picture, we can see a nuclear fusion generator, the world's largest nuclear fusion experiment in ITER Tokamak, in France. The fuel needed for nuclear fusion. First is deuterium. Deuterium is one of the two stable isotopes of hydrogen. The nucleus of the deuterium atom, called a deuteron, contains one proton and one neutron, whereas the far more common protium has no neutrons in the nucleus. Deuterium has a natural abundance in Earth's ocean of about 1 atom in 6,420 of hydrogen. Second is tritium. Tritium, or hydrogen-3, is a rare and radioactive isotope of hydrogen. The nucleus of tritium contains 1 proton and 2 neutrons, whereas the nucleus of the common isotope hydrogen-1 contains just 1 proton, and that of hydrogen-2 contains 1 proton and 1 neutron. The conditions for nuclear fusion. To achieve fusion, you need to create special conditions to overcome this tendency. Here are the conditions that make fusion possible. First, high temperature. High temperature gives the hydrogen atoms enough energy to overcome electrical repulsion between the protons. Under of that is fusion requires temperature of about 100 million Kelvin, approximately 6 times of hotter than sun's core. Second, at this temperature, hydrogen is a plasma, not a gas. Plasma is high energy state of matter in which all the electrons are stripped from atoms and move freely about. And third, the sun achieves this temperature by its large mass and the force of gravity compressing this mass in the core. We must use energy from microwaves, lasers, and ion particles to achieve this temperature. Second is high pressure. High pressure squeezes the hydrogen atoms together. They must be within 1 times 10 raised to negative 15 meters of each other to fuse. The sun uses its mass and the force of gravity to squeeze hydrogen atoms together in its core. We must squeeze hydrogen atoms together by using intense magnetic fields, powerful lasers, and ion beams. With the current technology, we can only achieve these temperatures and pressures necessary to make the deuterium-tritium fusion possible. Deuterium-deuterium fusion requires higher temperatures that may be possible in the future. Ultimately, deuterium-deuterium fusion will be better because it is easier to extract deuterium from seawater than to make tritium from lithium. Also, deuterium is not radioactive, and deuterium-deuterium reactions will yield more energy. Why do stars do nuclear fusion? The fusion of hydrogen nuclei uses up hydrogen to produce helium and energy. Hydrogen is the fuel for the process. As the hydrogen is used up, the core of the star condenses and heats up even more. This promotes the fusion of heavier and heavier elements, ultimately forming all the elements up to iron. And what happens to a star after nuclear fusion? The new star will continue to glow for millions or even billions of years. As it glows, hydrogen is converted into helium in the core by nuclear fusion. The core starts to become unstable and it starts to contract. The outer shell of the star, which is still mostly hydrogen, starts to expand. Has nuclear fusion been done? Yes. ITER is an unimaginably ambitious energy project. 35 years in the making, involving different participating nations worldwide, such as China, UE, India, Japan, South Korea, Russia, and US, with a goal of using fusion as an industrial-scale source of clean energy. When the plant comes online in Forges in the south of France, it will be the world's largest nuclear fusion reactor in this year 2021. Is fusion safer than fission? Yes, inherently safe but challenging. Unlike nuclear fission, the nuclear fusion reaction in a tokamak is an inherently safe reaction. This is why fusion is still in the research and development phase, and fission is already making electricity. That's all. Thank you for watching. I'm Junel and Victoria, your presenter for today.